All right, welcome back, my friends. This is William M. Briggs. What episode are we on? 36. I forgot to put the number up there. Not too good for a mathematician. Paradox lost and infinity. I'm going to put up there too. We're going to discuss briefly infinity today. So last week we covered basically the whole field of probability. This week we're just about to move into the more complicated stuff. We've been doing nothing but discrete things all along, very simple in concept anyway, mathematics. We're just counting, although that kind of mathematics is actually, I think, as I've been saying many times, the most difficult kind, because keeping track of everything, especially when problems go large and complex, is hideously difficult, made much easier with calculus and things like this. But the danger is assuming problems can be handled by calculus, by these type of infinities, as it's going to turn out. And we need to understand all of that. We need to understand we're going to move into what models are and what parameters inside models are and so forth. And then there's controversies around these topics because of failure to understand very simple probabilistic rules. We could wipe away all the Bayesian versus frequentist and controversies very simply and remove these paradoxes just with some very careful thought. Paradoxes are wonderful, by the way. They sharpen thought. They bring ideas into focus, and almost always in paradoxes, it's not a mistaken logic from the premises to the conclusion. It's a failure to understand that there are either missing premises, tacit premises, or a flaw in the premises themselves. And so that's what we're going to find out today. So let's have a quick, really simple, almost trivial review. We have an urn here, and inside the urn are 3 red balls and 5 black balls. And we're going to pull out a ball. What's the probability, based on that information, that the ball is red? So we'll just say red, the evidence that we have of the urn and so forth. Now, we proved a long time ago by the symmetry of individual constants. We proved what's called the statistical syllogism. And from that, we have the sort of uniform probability that it could be any of these balls. We're not talking about cause here. We're talking about our knowledge, and we have no knowledge. That's an implicit premise in this evidence right here. We have no knowledge. The implicit premise is we're not looking into at the top and seeing the red ball is sitting at the top, and we're going to grab the red ball and say, oh, here's the red ball. That's part of our tacit premises here. We have a mindless process where even a robot that doesn't understand what it's doing is just picking something out. What's the probability it picks out a red ball? And it's obviously going to be 3/8. No problem. Everybody understands things like this. And in fact, textbooks are filled with examples like this. But some people say that this symmetry of individual constants that we proved, 20 some episodes ago, that allow us to assign probabilities, uniform probabilities, in the face of ignorance, I guess you could say. We have no other knowledge except of the contents of the urn, and that's it. That's the only information we have. If we add information plus looky, well, that's not the same information at all, and the probability changes, because all probability is conditioned on the information that you assume. So here, according to some Draper, I'm going to do a couple of seeming paradoxes. There's a whole class of these seeming paradoxes, and they all take this kind of shape. So if we understand in the 2 examples I'm going to do for you, it's a very simple lesson today. I hope I don't go on and on about this and just prove to you something very simply. So we have a factory, he says, and they produce tiles. And these tiles are of length from 1 to 3 inches. They can be exactly 1 or exactly 3 inches or somewhere in between. Okay? And that, of course, means that the area of the tile will be 1 inch square to anywhere from 9 inch square. So that's our evidence, that's our information. Let me erase this up here. We don't need this urn anymore. We have the probability Oh, for instance, we can ask any kind of question we want. We want the probability that the length will be less than 1.5 inches, given this evidence, and that evidently will be a half. By our principle of the individual constants, we're going to assign a uniform probability. In other words, the probability less than 1 inch is 0, less than 3 inches, the probability of less than 3 inches is 1. The probability of less than any figure we set in here, less than 2 inches, for instance, will be 0.66, and so forth. We just assign a uniform probability to any length. All right, but then Draper argues, well, the area, half the area is 4.5 inches, so if we take the probability that we let the area be less than 4.5 inches, 4.5 square inches, he said that should be a half too. If we're going to just follow this principle of Laplace's principle, of insufficient ignorance, we have no other information except this bare information here. But then this seems to be a contradiction, because the probability of the area being less than 4.5 inches square, well, we just take the square root of that, and that's the probability of the length being less than or equal to, what is that, 212 or something inches. And that has to equal a half too, if we're following the same procedure of a uniform probability assignment. And this probability has to match this probability, and they don't, because the probability of 1.5 inches is supposed to be a half, and here we said the probability of 2.5 or 2.12 inches or so is a half. So there seems to be a contradiction, and probability is more difficult than we imagine. We can't just go assigning uniform probabilities. Well, the answer is no. The answer is infinity is a difficult thing, and we have just messed with infinity here. And infinity is a huge place. And I've warned us about infinity many times, and I'm going to warn us today, and I'm going to probably devote an entire class just to warning us about infinity. It's a tacit premise here. And remember, probability, let me erase all this, and I'm going to explain this again. In a more simple, we're going to blow this up. We're going to blow this up. Let's think about this factory in a more concrete way, the way an engineer would. This factory can manufacture tiles, let's see, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and all the other little dots in between. Let's just suppose we have a factory that does this. Now, the real factory will produce tiles that are not exactly 1 inch, they're not exactly 3 inches. There's going to be some fuzziness in this, because real machines cannot produce infinite gradations. This is the key right here. A machine cannot produce tiles on the continuum from 1 inch to 3 inches. In reality, it'll be something like this. The way I drew this is they look semi-uniform, and that's the way they would look to the naked eye. If we hold one of these tiles up, they would look fairly uniform. But of course, if we blow it up, we'd see all kind of irregularities. You know, some pieces would look like this, some pieces would look like this, and the whole thing would be somewhat chaotic and choppy. All right, and we would come to a point. It doesn't matter what the point is, but there will be a point at which we can no longer magnify this kind of a thing, and we're going to be left with blobs of this indiscriminate sizes that would look something, who knows what they would look like, but there would be discrete. It would be discrete, and it would be finite. So there's no loss of generality in thinking we could just think of this as 5 little atoms or something like this. Our tile can be made of 5 atoms big by 5 atoms wide. Now, if we want to have the probability of the length of this new tile, based on our new evidence, the length we could be less than, well, it would be 2.5, less than 2.5, given our new evidence. What is that probability? Well, I'll give us a little bit of a prime to indicate our new evidence right here. Well, we have 5 possible. I'm writing them up here more or less uniform, but they don't have to be. They can be any shape whatsoever. It doesn't make any difference to the argument here. I can have 2.5 is somewhere here. I can't have tiles that are less than 2.5. I can have tiles that are 1 or 2 or 3 or 4 or 5 in length. That's all I can have. I can't have anything else but that from that set. So this is evidently equal to less than 2.5 is evidently equal to the probability of less than or equal to, and that's going to be 2/5. Ooh, I'm running out of ink. Okay, now what about the area? The probability of the area was going to be, we want 5 times 5 is 25, or half of 25 is 12.5 units. I'm not putting units on any of these things. They don't have to be inches. They could be whatever unit you want. They have some unit though. 12.5 is this. And now we want to ask what this is. This is not us assigning a uniform probability. It is in a way. We're assigning the probability. We're still assigning a uniform probability to all of the possible outcomes. There's only 5 possible outcomes, and we're assigning a uniform probability to these. If we had different information and these different shapes and so forth, we would still assign a uniform probability. If each of these little blobs were, not quite manufactured perfectly, because we have no other information in E, or E prime, I should say. E prime just says all we know is the tiles come out and they're this size or that size, and that's it. Doesn't say anything about manufacturing constraints or how overlap might occur, and it's not possible to get a tile of this. Nothing like that. Nothing like that is in E prime. It's just the information we have. It can be this size or no other sizes, and that's it. So this one. So let's think about this. What are the possible areas we could have? Well, we could have an area of 1, and that corresponds to a length of 1. We could have an area of, an area of 4. That corresponds to, here's the length. We could have an area of 9, and that corresponds to a length of 3. We could have an area of 16, and that corresponds to a length of 4. Area 25, and a length of 5. So now, an area less than 12.5. What is an area less than 12.5? Well, that's a number we can only have one. The only possible areas are 1, 4, 9, 16, and 25. So that evidently is equal to the probability of the area being less than or equal to 9, given this evidence. And that, of course, equals 3/5. And that length is equivalent to, that area is equivalent to 3, which is not 2, and there's no contradiction. The probability of length being less than 3, the probability of the length being less than or equal to 3 in this particular scenario with this evidence is in fact 3/5. And these probabilities are now equal because these are the only possibilities. We have to keep track of the number of possibilities. So what we've done here is we've imagined this problem in a discrete and finite way. All right? And there's a huge problem when we move off to infinity, as we'll see. I don't know if we'll get to it this time or not, but I'm going to do one more. I'm going to do one more of these paradoxes here. And I hope you can see. Let me erase this here. It's going to still be discrete and finite. I can have as many of these tile things. They can be down to the molecule, they can be down to the quark, they can be down to whatever you like. I have a discrete and finite number of these. Quantum mechanics is all about discrete movements. It's really discrete movement. It's mechanics. Discrete mechanics is a better way to think of quantum mechanics. Rather, quantum. Quantum means exactly that. It means a quantum. You can have a single here and a single here and a single here. You can't have a continuum. So quantum mechanics backs this up too. There's no actual continuum. There's a potential infinity of things, and we'll come to that example, I hope. I'll be running out of time. So it's not the size. The size doesn't matter here. I can let this thing be any size I like. I can let the number of these digits go out as far as the number of possible ways I can carve up reality here to make tiles on this line from 1 to 3, as long as it's not the continuum, as long as it is finite, and you could do this same problem and you will see there's no paradoxes. There's absolutely no paradoxes in probability assignment that are reached as long as this thing is finite. Now, how big of a restriction is finite? The continuum, there seems to be, if we jump right to the continuum, which is an infinity larger than infinity, I will devote an entire topic to this because don't forget, probability is in our minds. It represents what we know about things. And we cannot even grasp simple probability, simple infinity, let alone the infinity of the continuum. We can prove its existence, we can prove a couple of things about it, but to actually have a feel for infinity, not possible. Not possible. Let me just introduce some numbers here to give you an idea. I've done this before, so let's do 10 exponentiated to the 10. Why, that's simple. Okay. Now let's do this. This is Knuth's up arrow notation. It's much more compact than writing exponentiations and so forth. Let's compute this very simple number. We're gonna up arrow 10 times, and that is equal to 10 to the 10 to the 10 to the 10. And we got 10 of these up here. And that number right there, we'll just call this A. This number here is so big, plug it into, look this up. Look this up, and maybe I'll put a link in the show notes here, the class notes. It can't be calculated. There's no computer that can calculate and store these digits. It cannot be done. It is already so monstrously large. Even 10 to the 10 is 100, and 10 to the 100 is a 1 with 100 zeros, and that's our second. And then we have a 1 with 100 zeros, and we have 10 to that. And so there has to be, and we're doing that 10 times in this simple operation here. We're just going to call this A, okay? Now, let's do this. We're going to do 10A. And how big is that? Why, that's 10 this many times, which we already can't calculate. 10, 10, 10, 10, 10, 10, 10, 10 almost just incomprehensibly. It's incomprehensibly large. We'll call this B. And we'll do this. 10, 10 to the B. We'll call it, for that, we'll call this, because there's such a thing as the Graham's number, we'll call this the Briggs number because it's a B. Little vanity here, never hurt anybody. Now, I want to ask you this question. How far is this number right here, 10 to the 10, 10 billion? How far is that from infinity? The counting infinity, 1, 2, 3, 4. How far is that from infinity? Well, let's draw a number line here. Here's 0. And we'll draw a little arrow out here. I don't have a board big enough to go out to infinity. Well, here's 0, and here's 10 to the 10. We'll call 10 billion right about there. Now, where is, on our fictional number line right here, here's 10 to the 10. How far away from that is infinity? Okay, don't answer. Let's have our number here, our 10, 10. We'll just draw it something like this. This is not necessarily to the scale here. Here's that. How far away is that number from infinity? This incomprehensibly large number here. I don't know. Let's do this one. It's somewhere going to be over here maybe. 10, 10 to the A. And somewhere over here is going to be 10 to the B, tetrated to the B. This number, and this number, and this number, and this number all share one important characteristic in that they are infinitely far away from infinity. There are these numbers that are so unimaginably huge that we could just write down this notation and not even barely grasp the true enormity of these things. I ask you to sit down and read the directions of this stuff and just wonder at how large these numbers are. And if we apply this math to these situations up here, it's not the continuum. the number of dots that I can have up here in 10 to the tetrated to the b here is not the continuum. And it's not even close enough, because even this infinity is infinitely smaller than the continuum. And we're asking our minds to assign probabilities to these things. So I'm going to spend a lot of time going over this stuff because we need to understand that we can't understand these things. It's just too difficult. All right? So there's no problem in using discrete and finite things, and there's no paradoxes if we have discrete and finite things. All right? But there could be when we make finite, we pull finite sets from infinity, whether that's the counting infinity or the continuum infinity, which is larger. That's where we have problems, and we're going to go over like Buffon's needle, Bertrand's paradox, and others once we get into what parameters are and all that kind of thing. We'll get into all this and see that we're really messing with forces that we cannot understand. And we're just glibly assigning probabilities to these things and saying, oh, it's no problem, we'll just do this. And the math works out. And we forget that no measurement that we could take, no observation that we could take can ever be infinite. It can never be more than discrete. So we're tying our very limited powers of discrete and finite measurements, and we're making grand claims about very, very large infinities that I don't think we can support. So here's another Draper thing. There's 3 balls in an urn, and they can be either white or black. White or black. And by the equal probability assignment, we don't know anything else about them, so we're going to give a probability of half. That is to say, the first ball we pull out, the probability of it could be a black ball could be a half, and the probability it could be a white ball could be a half, because that is to say, the probability that all 3 balls, let me put it this way, the probability that all 3 balls, ball 1, ball 2, ball 3, given this new set of evidence here, is going to be an 8. Because it's going to be 1/2 times 1/2 times 1/2. Because we don't know anything else that it could be either black or white. It has to be either one of those. It's like a coin flip. A coin flip, we know that there has to be, in a coin flip, we're not controlling the causes. We know that there are 2, and it must be only these 2, so we can assign a probability of a half. But then the Draper says there are 4 ratios of total black balls to all of the black balls. Well, those ratios, I'm going to have to get a new pen here. Those ratios are 1, in which it's all 3 of the black balls over the total number of black balls 3. It could be 2/3, it could be 1/3, or it could be 1, or 0 rather. Pardon me. There could be no black balls. Now he says the equal probability assignment here would give the probability of 1 ratio, the ratio equaling 1, oh boy, I have other colors, but I don't think they show up as well, given this evidence, is now 1/4. And it doesn't equal 1/2, and we have yet another contradiction. And I have another color here, but it's slighter than this. We have another contradiction, and therefore we can't go assigning equal probabilities, and probability is busted and so forth. But no. What he has forgotten is, well, there is only one way to get all balls black, and that's to have ball 1 black, ball 2 black, ball 3 black. There's only one way to get no balls black, and that's to have the first one white, the second one white, and the third one white. However, there are several ways to get 2 black balls. It's to have the first and the second one black, and the third white. It's to have the first black, the second one white, and the third, black. Or we could have the first one white and the second 2, the second ball and the third ball black. And there's 3 ways, again, we can get just 1 ball. We can have the first one, 3, 2 and 3. We could have the first ball can be black, the second white, the third white. We could have the first white, the second black, the third white. We could have the first and the second white and the third black. And there are now 8 scenarios here of possibilities for the bag, and only one of which is all 3 of the balls black, and we're back to a probability of 1/8 as before. And so there's absolutely no paradox. And so here it's not so much infinity that has caused us to go awry. It is that we have forgotten there's hidden tacit premises in here. It's not just that we have 2 out of 3 of the balls that are black. It's that there's various ways we can reach those combinations, 1 or 2 or 3 black balls. And so again, there's no contradiction. So the first one was a seeming contradiction because we were jumping right to infinity and coming up with absurd conclusions. And the second, but we found that as long as we stayed finite, which is absolutely no restriction whatsoever, because we could have numbers that are just mind-bogglingly, incomprehensibly large and still be infinitely far away from infinity, and we could solve our problems in this way. So there's absolutely no problem doing that. And this one here is just because there's tacit premises forgotten. So all of these probability paradoxes, we're going to find out, fall into one of these 2 camps. I haven't seen anyone that hasn't yet. It's going to be very important for entropy, the idea of entropy and information and all this kind of thing. And again, we're going to be dealing with infinities and so forth, and parameters and models, and how probabilities are assigned to parameters and models and so forth. The solution is going to be, don't start out at infinity. Unless you've worked out from previous work that you know that infinite approximations are going to be just fine for you. We've already done this before. We saw that just jumping to infinity is not very helpful. We start finite, we start discrete, and we can go to the limit. We can let the math be easy, and we can have nice approximations. I mean, we don't have to necessarily nail exact numerical probabilities for every single thing we do. So using infinite math is no problem, and much to recommended. But just starting at infinity, which is what most problems do, and just tossing infinities around like it's no big thing, that leads to all kind of problems, which we will see as we continue this course. That's it for now. I'm going to have homework. I'm going to give a homework problem that's along these lines that you'll see in the write-up. It's going to be either at wmbriggs.com or wmbriggs.substack.com. And I think after this, we're finally moving into causality, and then we'll finally move into models and get to the really good stuff that people have been waiting for. It only took about a year to get to the good stuff. So there we have it. Thanks very much for listening.